Hello everyone, and we're back with Mr. Abdul Wahab, that is myself of course, and we're going through the second SAT practice test. We've gone through the first four texts on the SAT, and now we'll be tackling the fifth one. The aim of this series of videos, I mean, it's intended as something like a course actually that you could sit down and watch and actually try to enjoy as you study for your SATs. The aim of this course is to actually show everyone, all high school students who are taking their SATs anytime soon, that the SAT is not as intimidating or as hard as many people make it seem, especially the new SAT. And this is a tutorial concerning the new SAT. And it's concerned with the English part, of course. I'm an English teacher, and I'm trying to help as many students as possible actually ace their SAT exams. I'm going to try to show you that it's actually quite feasible to go through each and every text and read it, comprehend it, understand it, and be able to actually answer all of the questions concerned with it completely correctly, with no mistakes, virtually no mistakes. And so this is not impossible to do, and so I think that with a lot of hard work, and if you put enough time into it, you could actually get at least uh, 700 over 800 on your English part. And so as I said, we've done the first four texts, and now we're tackling the fifth. We've gone through the literature text, the U.S. history text, the social studies text, and so on. This is the science text. It's a scientific text, and as we've said before, do we need to know any specific scientific information to be able to go through this text? Absolutely not. You don't need to know anything. You don't need to memorize information to actually do this. The only thing that you need to be able to do is actually read the text, understand it, comprehend it completely, analyze it, and be able to read the questions and answer all of them correctly. And that's it. You don't need to know anything about any scientific topic. I mean, some background information, of course, can be helpful, but sometimes it could actually confuse you because you might know something and it could be a false piece of information, or you think you know something about the topic, and it would actually interfere with what you're reading on the text. So the main thing that we rely on whenever we're solving an SAT text is we don't take into consideration anything which is not mentioned in the text. We're analyzing this text, and only these words are concerned with the questions below. So questions 43 to 52 are based on the following passage and supplementary material. You should expect a graph following the text, and as usual, the piece of advice I always give: read the intro, read the caption above the actual text. It gives you an idea concerning what you're about to read, and you want to form these main ideas or these generalizations about the text early on, so you would know what you're looking for. So this passage is adapted from Jeffrey Giller, Long a Mystery, How 500-meter high undersea waves form is revealed. So the author of this text is discussing an undersea kind of waves that's 500 meters tall, so that's quite high. He's discussing how they form, and that they've actually finally revealed how they shaped or come into shape. So let's begin. Some of the largest ocean waves in the world are nearly impossible to see. Interesting. Unlike other large waves, these rollers, called internal waves, do not ride the ocean surface, so they don't appear on the surface. So we're not talking about something like a tsunami or whatever. This is happening inside the ocean, probably. It's an internal wave. Instead, they move underwater, undetectable, without the use of satellite imagery or sophisticated monitoring equipment. So without satellite imagery or sophisticated monitoring equipment, we can't actually detect them. Despite their hidden nature, internal waves are fundamental parts of ocean water dynamics, transferring heat to the ocean depths and bringing up cold water from below. So those are two important things that they do, these internal waves. They transfer heat to the ocean depths and they bring up cold water from below. We're going to see how. As they can reach staggering heights, some as tall as skyscrapers. Because these waves are involved in ocean mixing, and thus the transfer of heat, understanding them is crucial to global climate modeling. So if you're working on global climate modeling or understanding the global climate or the climate of the globe, you need to understand how the internal waves function, how they form, and how they affect everything around them, says Tom Peacock, a researcher at the Massachusetts Institute of Technology. Most models fail to take internal waves into account. So whatever models we have, or most of the models we have today, they don't take into account internal waves. And according to the author, of course, this is a huge mistake. If we want to have more and more accurate climate models, we have to be able to capture processes such as this, Peacock says. So basically, if you want to understand, or if you want to get accurate models or predictions concerning global climate, if you want to have a better understanding of global climate, you need to take into consideration or bring into the picture these internal waves. So Peacock and his colleagues tried to do just that. Their study, published in November in Geophysical Research Letters, and as we said, when you have an italicized words, that means that this is the name of a magazine or a periodical or a newspaper or a book. This is probably a scientific magazine. Focused on internal waves generated in the Luzon Strait. So they are studying internal waves, okay, generated in the Luzon Strait, which separates Taiwan and the Philippines. Internal waves in this region, thought to be some of the largest in the world, can reach about 500 meters tall. That's a staggering height. That's the same height as the Freedom Tower that's just been built in New York. Now, of course, why did the author give this imagery? To show us how tall these waves can actually be. So this kind of imagery serves a role, of course, in the text, and you might be asked about it later on in the questions. You should anticipate questions like, what does this choice of words help the author accomplish? Although scientists knew of this phenomenon in the South China Sea and beyond, they didn't know exactly how internal waves formed. To find out, Peacock and a team of researchers from MIT and Woods Hole Oceanographic Institution worked with France's National Center for Scientific Research using a giant facility there called the Coriolis platform. So we have lots of people working together, okay? Researchers from MIT, Peacock, Woods Hole Oceanographic Institution, and they're working with France's National Center for Scientific Research. So that's a lot of people working on this. So this is probably a very important issue. The rotating platform, the Coriolis platform, about 15 meters in diameter, turns at variable speeds, at different speeds, and can simulate, it can imitate Earth's rotation. So that's a very interesting device. It also has walls, which means scientists can fill it with water and create accurate large-scale simulations of various oceanographic scenarios, okay, of things which could happen in the real world. So Peacock and his team built a carbon fiber resin scale model of the Luzon Strait, including the islands and surrounding ocean floor topography. So they are basically building a model that resembles or copies the Luzon Strait with all of the details included. Then they filled the platform with water of varying salinity. Salinity is the amount of salt that you have in water, to replicate, again, to copy the different densities found at the strait. So again, they're trying to build a model that accurately represents or imitates what we would find in the actual Luzon Strait between the Philippines and Taiwan. So they filled the platform with water of varying salinity with different with water different the waters of different degrees of salinity, which is the amount again of salt that's dissolved in the water, to replicate or to copy the different densities found at the strait, with denser, saltier water below and lighter, less briny water above. So the water which is saltier or denser is below, and the lighter or less briny, less salty water is above. Small particles were added to the solution and illuminated with lights from below in order to track how the liquid moved. So this is a very sophisticated process. Finally, they recreated tides, waves, using two large plungers. A plunger comes from the word plunge. When you plunge something, you bring it down, usually into a body of water. So a plunger is supposed to be a very huge device, probably something like maybe a hammer that they would bring down into the water in a vertical kind of motion to see how the internal waves themselves formed. So the Luzon Strait's underwater topography, how it looks like, that's the topography, with a distinct double ridge shape, turns out to be responsible for generating the underwater waves. Now, first of all, before I continue, I just want to tell you that a strait is usually a body of water that passes between two bodies of land. So the water is passing basically through here, okay? And those are the two ridges they're talking about, okay? So the Luzon Strait's underwater topography with a distinct double ridge, okay, shape turns out to be responsible for generating the underwater waves, the internal waves. As the tide rises and falls and water moves through the strait, colder, denser water is pushed up over the ridges into warmer, less dense layers above it. So this goes in line with what was said at the beginning of the text, that the internal waves bring up cold water from below. This action results, what are the results of this action? In bumps of cold water trailed by warmer water that generate an internal wave. So basically you have the cold water coming out, and then it goes back down, and then the warmer water goes back up, and then you have this circular kind of motion. And that's how the internal waves are forming. As these waves move toward land, they become steeper, higher, at a steep angle. Much the same way waves at the beach become taller before they hit the shore, until they break on a continental shelf. Now this is a bit wordy, continental shelf, but basically what it means is a piece of land. A very huge piece of land, if I may say. So the researchers were also able to create a mathematical model, a model in numbers, that describes the movement and formation of these waves. Whereas the model is specific to the Luzon Strait, so the model they made is specific to the Luzon Strait, to this area they were studying. It can still help researchers understand how internal waves are generated in other places around the world. So although the model was built specifically to study the internal waves in the Luzon Strait, other scientists could use the same model to study or to try to understand how internal waves are generated in other places. So it could actually help globally around the world, of course. So eventually this information will be incorporated, okay, taken into global climate models, making them more accurate. So by the introduction or the incorporation of this information into the global climate models, we're going to have more accurate climate models, as again was suggested by the author at the beginning of the text. It's very clear within the context of these global climate models that internal waves, again he's repeating the idea mentioned at the beginning, play a role in driving ocean circulations. So that's the text. It's I wouldn't say it's specifically challenging. There are a lot of details in this section where they actually describe how the process happens, how the internal waves form. And it's not really too hard to understand. The only thing that you need to remember is that the cold water is pushing itself up above the hot water, then plunging back down because the hot water is going back up because it's less dense, so it's gonna try to go back up. And then the cold water again is going back up. So there's this circular motion, okay? And why am I using the word circular? Because this was again mentioned in the text. So I could rely on it to try to understand what's happening in the formation of the internal waves. Now, right below on the next page, you have this graph. And for some of you who think that graphs are hard to read, I would suggest that you take each axis on its own and try to understand what they are introducing. So the vertical axis on the left, this is the depth below surface in meters. So as you go up, you're going towards the surface. That's 0, that's the surface, okay? And 40, that's 40 meters below the surface. 80, 120, 160, so that's the deepest depth. Now, the horizontal axis on the bottom, this basically shows us, okay, the horizontal axis on the top and the bottom, they represent basically the passage of time from or across 24 hours. And the title, of course, is Changes in Depths of Isotherms in an Internal Wave over a 24-hour period. When you see an asterisk, this tiny star, that means there's a note at the bottom. So isotherms are basically bands of water of constant temperature. And we have this little graph at the bottom as well, okay? The dashed line represents water that is 13 degrees Celsius. The gray line represents water that is 11 degrees Celsius. The dotted line is 10 degrees, and so the dark line, the dark black line, is 9 degrees Celsius. So one thing we can see immediately from the graph is that the colder water is at the bottom. The warmer the water gets, the higher it goes, and so on. And of course, the colder the water is, the deeper it goes. So let's begin with the questions. The first paragraph serves mainly to. What does the first paragraph do? If we go back to the first paragraph, some of the largest ocean waves in the world are nearly impossible to see. Unlike other large waves, these rollers called internal waves do not ride the ocean surface. Instead, they move underwater, undetectable without the use of satellite imagery or sophisticated monitoring equipment. Despite their hidden nature, internal waves are fundamental parts of ocean water dynamics, transferring heat to the ocean depth and bringing up cold water from below. And they can reach staggering heights, some as tall as skyscrapers. So let's take a look at the options we have. Explain how scientific device is used. Definitely not. They didn't explain how a device was used. Note a common misconception about an event. They're not discussing a misconception. They are explaining a phenomenon. So describe a natural phenomenon and address its importance. Well, this looks good. This looks like the right answer. Present a recent study and summarize its findings. Again, not exactly. They didn't present a recent study in the first paragraph. So C is probably the best answer. Let's take a look at 44. As used in line 19, capture is closest in meaning to, let's go back to line 19. If we want to have more and more accurate climate models, we have to be able to capture processes such as this. Capture processes such as this. So I would say just from reading the sentence that what they mean by capture is probably to record in one way or another, or to actually follow up with something, or to be able to monitor such a process. So let's go down to the options we have. Control. Not exactly. We're not trying to control the process. We're trying to record it. This looks good. Secure. We're not securing anything, and there is no absorption happening. So B looks like the best answer. 45. According to Peacock, the ability to monitor internal waves is significant primarily because, now we could remember that he said that this is extremely important because it's gonna help us construct more accurate climate models. That's what I remember from the text, and you should be able to remember a detail like this because it was repeated a lot in the text. So it will allow scientists to verify the maximum height of such waves. That's not why it's significant. That's not why it's primarily or most importantly significant. It will allow researchers to shift their focus, to change their focus to improving the quality of satellite images. That's not why it's significant. Again, they don't want to improve the quality of satellite images. I remember that the text said, and you could go back to the text, what they want is to build more accurate climate models. The study of wave patterns will enable regions to predict and prevent coastal damage. This idea was not presented in the text at all. The study of such waves will inform the development of key scientific models. Well, yes, this is definitely the answer. The study of the internal waves will inform the development of the key scientific models, which are again the climate models. Now, which choice provides the best evidence for the answer to the previous question? We need to go back to the text and find the part which talks about why it's important for global climate models. And so we have 1 to 2, 4 to 6, 17 to 19, 24 to 26. 1 to 2 doesn't really mention global climate models. 46 doesn't do so either. And 17 to 20, if we want to have more and more accurate climate models, we have to be able to capture processes such as this. So, I mean, I could just save myself some time because I know that this is the part that talks about the point mentioned in the previous question, which is again the global climate models. So I could move on. As used in line 65, devise most nearly means. Let's go back to line 65. And also when you have a question like this, asking you to figure out how a word is used and or what is the meaning or the closest meaning associated with a word used on a specific line, go back to the line and read it just to make sure how it was used. Because you could have many synonyms for the same word. You need to know which meaning was specifically used. So devise line 65. Researchers will also be able to devise a mathematical model that describes the movement and formation of these waves. Okay, so I would say that the word devise here means to create or to build. Okay, so let's go down to the options we have. So we've got create. That looks good. Solve. They're not trying to solve models. They're trying to build or create models. Imagine. Begin. No. A is clearly the best answer that we could choose. Now, based on information in the passage, it can reasonably be inferred that all internal waves reach approximately the same height, even though the locations and depth of continental shelves vary. Well, first of all, their height is not caused by the depths of the continental shelves. Now, in any case, not all internal waves reach approximately the same height. They could reach 500 meters in height, but nothing was said about the fact that they have a uniform height. So you could have internal waves which are maybe 50 meters tall, 100 to 50. They could get to 500. So the point mentioned in A is not actually accurate. B, so it can be inferred that all internal waves may be caused by similar factors, but are influenced, they are affected by the distinct topographies of different regions. Well, that seems kind of logical, but I'm going to read on to see if there's a better answer. That all internal waves can be traced to inconsistencies in the tidal patterns of deep ocean water located near islands. this point is not mentioned in the text, that we can trace or we can infer that all internal waves, that they can be traced to inconsistencies in the tidal patterns of deep ocean water located near islands. You have many details here that were actually not mentioned in the text, especially the point about the islands. That all internal waves are generated by the movement of dense water over a relatively flat section of the ocean floor. Again, nothing such as this was mentioned in the text. So I'm going with B, and I'm pretty confident of my answer. 49. Which choice provides the best evidence for the answer to the previous question? Let's take a look. So we have 29 to 31. Let's see what's 29 to 31. Although scientists knew of this phenomenon in the South China Sea and beyond, they didn't know exactly how internal waves form. This has nothing to do with our answer before. If you go back lines 56 to 58, let's see what they say. As the tide rises and falls and water moves through the strait, colder, denser water is pushed up over the ridges into warmer, less dense layers above it. Okay, interesting pieces of information, but again, they have nothing with the conclusion or the inference we made here. 61 to 64. As these waves move toward land, they become steeper or higher, much the same way waves at the beach become taller before they hit the shore, until they break on a continental shelf. So they're just describing how the waves finally take shape, and then they finally collide with the continental shelf, or basically the land. Now, let's check and see our last option, 67 to 70. Whereas the model is specific to the Luzon Strait, it can still help researchers understand how internal waves are generated in other places around the world. So, even though the model was made specifically for the Luzon Strait, it can still help researchers understand how internal waves function in other places. So it may be caused by similar factors, but it's influenced by distinct topographies of different regions. So different regions affect, which are again other than the Luzon Strait, these distinct topographies, they might affect, okay, or influence the factors which create or form the internal wave. So I'm going with D. It's the answer which is most connected to our answer in the previous one, in 48. Now in the graph, which isotherm, which level of water, if you go back to isotherm, it's bands of water of constant temperatures. So every line is an isotherm, okay? So, which isotherm displays an increase in depth? Increase in depth, that means it went deeper below the surface during the period 1912 to 2024. So here's 1912, 2024. Which one went deeper? Okay, between this part. So the 13 degrees band of water or isotherm, this is going down. The 11 degrees isotherm is going up. The 10 degrees isotherm is going up as well, and the 9 degrees isotherm is also increasing. So the best answer is the 13 degrees isotherm. So I'm going with D. Which concept is supported by the passage and by the information in the graph? Internal waves cause water of varying salinity to mix. The graph does not display bands of water of varying salinity. So it displays water of different temperature. And if we go back to the graph, these isotherms or bands of water, they're not mixing so much as changing depth. They're going up and down, but they're not actually mixing. So you're not seeing the 10 degrees isotherm going up above the 11 degrees or the 13 degrees isotherm. So they are varying in depth, but they're not mixing. So Internal waves push denser water above layers of less dense water. Again, this is not presented in the graph. Internal waves push bands of cold water above bands of warmer water. Again, we can clearly see that colder water in this graph is not actually pushing up above warmer water. Internal waves do not rise to break the ocean's surface. Let's take a look. So all of those are internal waves, and they're going up and down, but they're not breaking the surface. And that's true. So our answer is D. How does the graph support the author's point of view that internal waves affect ocean water dynamics? How does it support the author's point of view or opinion that internal waves affect, influence ocean water dynamics? How the ocean water moves and reacts to everything around it. So it demonstrates that wave movement forces warmer water down to depths that typically are colder. So if we go back to the text, to the graph, we can see, for example, that the isotherm of 13 degrees Celsius dropped down to the level which was previously occupied by the 11 degrees isotherm. And the 11 degrees isotherm also plunged down to where the 10 degrees isotherm was. So internal waves of certain temperatures are dropping to depths previously occupied by isotherms of lower temperatures. So if we go back to A, it demonstrates that wave movement forces warmer water down to depths that typically are colder. Well, this is true. Let's check the rest. It reveals the degree to which an internal wave affects the density of deep layers of cold water. Again, the graph doesn't talk about the density of the water, but the temperature. Now, of course, the temperature and the density are connected to each other, but we're going to stick with the temperature. So anything that says warmer or colder. It illustrates the change in surface temperature that takes place during an isolated series of deep waves. We're not discussing the surface temperature, but the temperature of the isotherms, again, the bands of water that have a constant temperature. Sorry, apologize. So it's not C. It shows that multiple waves rising near the surface of the ocean disrupt the flow of normal tides. The graph does not show the interaction of internal waves with surface waves. This doesn't exist on the graph. So our best answer is A, and I'm going with A. And so that's it. I mean, of course, when you're doing the SAT, you're going to be going through it much faster. We're taking our time trying to explain stuff, trying to explain and show that they're not as difficult as some might think they would be, that they could actually be tackled quite easily by any person who just sits down and actually thinks about each and every option that he's given in each and every question. They try to trick or use words to confuse the reader. I would actually amend my statement. They're not trying to confuse you as much as they're trying to see how attentive you are to details and minor changes in words that cause minor changes in meanings. So, as I usually do, we're going to go through with the correction of these answers. I have the answer key right here, and you could get this answer key and the exam, of course, from the College Board website. They're available for free, of course, and I'll give you the link below once we go through them. So we are on question 43. Let's go down to 43. So 43 is C, 44 is B. That's C, sorry. That's C, and that's B. 45 and 46, D and C. So that's D, and that's C. 47 and 48, A and B. So that's A, and that's B. 49 is D, 50 is D as well. So 49 is D, and 50 is D as well, of course. And finally, 51 is D, and 52 is A. So here's D, and here's A. So again, I truly hope I was able to help you go through this practice exam, and I hope I was able to demonstrate how you could tackle these questions and answer them with almost great ease. Again, don't be intimidated by the exam. Don't be intimidated by tough words or multisyllabic words or topics that you're unfamiliar with. You are going to come across topics that you're not familiar with, but that doesn't mean that you can't read the text and understand it and answer these questions correctly. I mean, I personally know nothing about tides or oceanography or any of these stuff. And again, you don't need to know scientific information to go through the SAT exam and answer each and every one of those questions. You just need to be able to read the text and make certain inferences and conclusions about it. If you like how we're doing or how we're solving these exams, if you feel like they are helpful, if you feel like they could actually benefit people and students doing their SATs, please share this video with anyone you know that might need help on their SATs. And I really hope that I helped. Stay tuned for some more videos on the SAT, the reading and comprehension, as well as the language and writing parts. We're going to be going through as many parts of the SAT exam as possible in the shortest shortest period of time that we can. Thank you very much for watching. Again, if you liked what you saw, like, subscribe, and share, please. And I hope that you learned something useful today. Thank you very much.